Hello, welcome back. Today we will be continuing our lecture regarding the course Aerospace Propulsion. My name is Sai Krishna from the Department of Aeronautical Engineering from the Institute of Aeronautical Engineering. So, in the previous class, what we have discussed is basically regarding the thermodynamics of a rocket engine, and we will be considering the same thermodynamics in order to derive the thermodynamics thrust equation and see few characteristics regarding that thermodynamic thrust equation. Now, from the previous what we have done, we have derived, we have come out till this part where the expressions, right, particularly related to the effective exhaust velocity and the mass flow rate m, which are derived under thermodynamics under my previous lecture, and substituting, and after few manipulation and cancellation, what we are getting, the thrust equation, right, or the force, which is also the fundamental thrust equation. Now, based on this, right, based on this, it contains of three terms, particularly a Newtonian thrust that is related to the mass ejection, particularly related to the exhaust gas, and second one is the accelerating force that is leaving from a static pressure to the exhaust stream as it leaves the nozzle, and the third is the retarding force, which is by the ambient pressure. We will see these components. First one will be your Newtonian thrust, that is represented by Fr, right? The second will be your accelerating force. That force is related to your pressure at the combustion chamber and the cross section area and the pressure ratios. And the third, sorry, not till here, till here, and a small retarding force which is due to the ambient atmospheric conditions, right? These three constitute our total thermodynamic thrust equation. Now, upon this, now the same equation no longer consists the terms related to combustion, particularly in terms of molecular weight as well as the temperature, but these terms under individual expressions for mass flow rate as well as exhaust velocity do cancel and are now subsumed into the combustion chamber and exhaust pressures. Now, the mass flow rate depends basically on the density, which is proportional to the square root of molecular weight over the temperature, and the velocity on the other hand depends on the energy contained in the hot gas, which is determined by the square root of temperature over molecular weight. Now, this doesn't mean that the temperature and the molecular weight are not important in the performance of rocket motors. So, the thrust is made up of the mass flow rate, which is predominantly determined by the throat area and the pressure in the combustion chamber, and the exhaust velocity, which depends on the temperature and the molecular weight. Now, the former factor mainly determined by the size and the shape of the rocket motor, which is, and the later is determined by the propellant combination, right? So this we will discuss. Thrust is made up of two contributors. First one will be your mass flow rate, and second one will be your throat area. Now, the mass flow rate, which is predominantly considered by throat area and pressure in the combustion chamber, whereas the exhaust velocity is dependent on what? Basically temperature and molecular weight, right? These are the dependent factors on which our previous, particularly the thrust, depends. Now, under these, the first, which is nothing but my mass flow rate, is determined by the size and shape of the rocket motor, which is directly towards my throat area. Whereas the second one is dependent on the propellant combination in what we use, as well as the conditions in which propellant is being burned. That is related to my temperature that is being generated, as well as the molecular weight. Now, the product of throat area and the chamber pressure, which appears at the beginning of the formula, is a fixed parameter which determines the size and other mechanical design properties of rocket. Now, the throat area determines the dimensions, while the pressure determines the whole host of requirements from the strength of the chamber walls to power the turbo pumps. Right? Based on the chamber walls material, which are again used to identify the pressure or the power through which the turbo pumps are to be powered on or to be worked in order to carry out the required or to maintain the required pressure at the combustion chamber. Now, the main parameter in any rocket motor sizing is the throat area, which is denoted by A star. Now, the defining property of the nozzle is an exit area, as well as the shape of the nozzle, which can be expressed in the dimensionless way as an expansion ratio denoted by AE to A star, where A is my exit area and A star will be my throat area, which is nothing but my expansion ratio. Now, this depends on the expected ambient pressure, PA. Now, in order to maximize or maximum efficiency, the PE, particularly the pressure at the exhaust, should be equal to the ambient pressure. As well as this value can be controlled by the expansion ratio by changing the cross-sectional areas. Now, an expression for expansion ratio can be derived in the ratio from the above expressions for mass flow rate per unit area at the throat as well as the exit plane. Now, the mass flow rates cancel, leaving after some rearrangement, we can rewrite it as the expansion ratio AE by A star is equals to the square root of the values. Now, let us understand this. What is the effect of expansion ratio in order to the pressure ratio? From the formula, we can understand that, right, the expansion ratio is inversely proportional to the pressure ratio, right? Rather than this gamma is the same, it will be directly, inversely proportional to your pressure, exhaust pressure to the combustion pressure, particularly pressure ratio. Now, let us try to understand a graph. Now, figure shows the ratio plotted as a function for the different pressure ratios for 1.1, 1.2 as well as 1.3, right? For gamma equals to 1.1, 1.2 as well as 1.3, for the what are the pressure ratios as well as what is the expansion ratio that we can find. Now, the value of 1.2 is about average for many rockets, and this figure can be used to read off the pressure ratio for a given rocket nozzle, given the expansion ratio or the vice versa. And when trying to establish the correct expansion ratio for a given ambient pressure, right? Let us understand this graph a bit so that whenever we are designing a rocket, particularly rocket motor, what happens for a particular expansion ratio for a given value of gamma, which is equal to 1.2, which most of the rockets do have, for a given pressure ratio, let's say for 0.1, we can calculate the expansion ratio, right? For a given pressure ratio, we can calculate the expansion ratio, or for a given expansion ratio, but really we are fixing our nozzles first. For given expansion ratio, we can calculate the pressure ratio as and when needed. Now, There are two other parameters of the rocket motor which can be defined and which are helpful in calculating the performance. These are your thrust coefficient, which is denoted by C suffix capital F, and a characteristic velocity, which is denoted by C star. Now, the thrust coefficient, which represents the performance of the nozzle, the characteristic velocity, that of the propellant as well as the combustion. Now, the total thrust coefficient is the ratio of the thrust to the notional force defined by the product of the combustion, chamber pressure and the throat area. Now, it is defined by a relationship that Cf or C suffix F, thrust coefficient, equals the force or the notional force that is being generated to the combustion chamber pressure and the area, particularly the throat area. Now, using the same formula and rewriting, it gives you the force in terms of the thermodynamic thrust equation. Now, in this, and having divided it through the PCA, which is nothing but by this term, what we are getting, Cf or thermodynamic force, thermodynamic thrust, thrust coefficient can be rewritten in terms of the thermodynamic thrust equation in the form. Now, the first expression is the ratio of quantities which can be measured during the firing of a rocket motor, whereas the combustion chamber pressure is measured by a sensor or in a chamber, and the thrust is directly measured during the static test fire bed, and the throat area is the dimension of the nozzle. Now, and the second expression is a theoretical calculation based on the thermodynamics. This immediately shows how coefficient can be used to estimate the departure of an actual motor from its theoretical efficiency. In the same way, it can be used for a first estimate of nozzle performance based on theory. Now, thus selected a throat area as well as a combustion chamber pressure, the effects of expansion ratio for a particular ambient pressure conditions can be well calculated. Now, the thrust coefficient depends on the ambient pressure as well as is larger for vacuum conditions and for finite ambient pressure. For vacuum, PA, that is the ambient pressure, and the coefficient is given by the equation, where thrust coefficient equals to the terms for the Newtonian force plus the pressure and the cross-sectional or the expansion ratio. Now, comparing the two expressions, this as well as this, what we can rewrite in terms of Cf or the thrust coefficient is equals to thrust coefficient at vacuum minus the area as well as the pressure ratios. Now, these two values, the two ratios are often given for the rocket engine, so this can be useful to determine the thrust coefficient at a particular rocket engine. Now, and in order to appreciate the thrust coefficient, we can set PE equals to 0, which is nothing but exhaust pressure, in which case the expansion is assumed to be perfect, means the expansion ratio is equals to 0, and the rocket is operating under vacuum. So, which gives again the thrust coefficient in this form. And for gamma equals to 1.2, it takes a value of thrust coefficient takes a value of 2.25. Now, this can be now compared with the notional motor, particularly any motor here which doesn't have any nozzle. So, the exit pressure is the same as the throat pressure and the exit area is the same as the throat area. So, from another differentiation, the mass flow equation of the throat pressure can be determined in terms of pressure ratios to a certain value. Now, the cross-sectional, particularly the expansion ratio, is of course equal to unity, and a substitution for the same for the thrust coefficient gives in an absence of nozzle, the thrust coefficient as this. Now, the exit pressure is no longer 0. Hence, the presence of second term, particularly the coefficient in the absence of nozzle, takes the value of 1.24 for gamma equals to 1.2. Thus, a rocket motor without any nozzle still develops thrust as it experiences, shows simple to your toy balloon. As let's consider a small example. For a toy, particularly a balloon, this is the gas that is inside it. Now, as soon as we release it, it tends to get out of the small inlet way that has been developed. Now, through this what happens? Whatever the gas that is being in is pushed out by the atmospheric pressure, right? Which creates the exhaust pressure. Now, in our case, for any balloon, we will not be having any nozzle. It will be having only throat, through which the gases, particularly the gases which are inside, do move on. So, based on this, what we are telling, it develops certain amount of thrust, although it's not having a certain nozzle. Nozzle will elaborate or expand the amount of gases, converting itself into supersonic velocity and enhancing the thrust. But however, the thrust developed nearly a factor of 2 or lower because much of the energy stored in the gas is being wasted. Now, and using the thrust coefficient, we can also re-examine the notion that the maximum efficiency is achieved for a nozzle when the expansion ratio is such that the exhaust pressure equals the ambient pressure, right? So, maximum pressure in a nozzle, right? Nozzle is achieved when the ratio of exhaust pressure, particularly P by Pc, is equals to Pa, right? Maintaining this pressure ratios will give us the maximum efficiency. Now, let us understand a small graph. Now, the figure shows the thrust coefficient has been plotted against the expansion or the area ratios, and for the different values of ratio of combustion chamber pressure to the atmospheric pressure, it can be seen that atmospheric pressure value, the thrust coefficient peaks at a particular expansion ratio. Rather, after later, it drops down. Let me just reiterate. Area ratio, the graph has been plotted with respect to the thrust coefficient to the area ratio. Now, for certain value of gamma, which is 1.2, and varying pressure ratios. Now, what happens as the, let's say, as the area ratio increases, for a certain pressure ratio, at some point, right, or at some thrust coefficient, there will be maximum pressure ratio, right? Each atmospheric pressure value, the thrust coefficient peaks, right? The thrust coefficient is at peak for a certain period. Later on, it gets dropped off. Now, upon inspection, we can see that the expansion ratio at the peak at which it produces the exhaust pressure is equal to the atmospheric pressure, and the maximum thrust that is being developed when the exhaust pressure is equal to the ambient pressure, and the thrust coefficient is thus the measure of the efficiency in which the nozzle extracts energy from the hot gases in the combustion chamber. So, in other terms, the thrust coefficient is nothing but a simple measure of efficiency in which the nozzle extracts energy from where the hot gases that are present in the combustion chamber. Now, in order to determine a characteristic velocity which measures the efficiency of conversion of thermal energy into combustion chamber high velocity exhaust gas, a characteristic velocity is a measure that measure the efficiency of conversion of thermal energy that is being generated by the combustion into high velocity exhaust gas. Now it is defined by a ratio of a notional force given by the pressure in the combustion chamber, particular combustion chamber pressure integrated over the throat area, now divided to the mass flow rate, which gives in the form of C star, which is nothing but my characteristic velocity, PC combustion chamber pressure, A star is the throat area, and M is my mass flow rate. Now it has the dimensions of the velocity, and again is being based on the measurable quantities. Now its thermodynamic form can be rewritten as this given, square root of. Now the characteristic velocity depends on the temperature as well as inversely on the molecular weight, right? And again, the comparison between the expected and the actual values can be used to assess the performance of the motor. Particularly, characteristic velocity can be used to estimate the expected performance of the new motor design. Particularly, a characteristic velocity, a figure which shows characteristic velocity as a function of combustion temperature and molecular weight of exhaust gas, and for plotting purposes we have undertaken those into a single parameter, particularly a combustion parameter. Now as we can see, for gamma equals to 1.2 for a standard value, as the combustion parameter increases, the characteristic velocity also increases linearly, right? Now a typical value of a characteristic velocity is around 2000 meter per second, particularly for liquid oxygen or liquid hydrogen engines which have a combustion parameter of approximately 16, but for the solid propellants they are about 10. And the graph which we have seen already deduced, for high exhaust velocities are associated with high temperature and low molecular weight, right? In order to get my higher characteristic velocity, the temperature should be higher but the molecular weight should be lower. This particular combustion property will enable us to get higher speeds of velocity for the rocket. Now, and in order to design rocket engine, the choice of propellant of combustion will define the characteristics of a characteristic velocity. The effect of the nozzle, particularly expansion, can then be added to the thrust coefficient. And the choice for high temperature combustion may be limited by structural properties of combustion chamber material. Right? Let us elaborate small a bit. Now, whenever we are designing a rocket engine, a particular choice of propellant combination will define the characteristic velocity. In what way? Because from the equation or from the combustion parameter, what we can put is basically from the combustion parameter, what we can get basically is the characteristic velocity, particularly C star, is directly proportional to the temperature of the combustion, but inversely proportional to the molecular weight. So, whenever a suitable combination of propellants is being considered, the propellant combination which gives less molecular weight of exhaust gases with higher temperature of combustion will give you a good characteristic velocity, right? A good characteristic velocity which is defined for better identification of the rocket engine. Particularly, the effect of nozzle, right, and expansion can then be added using thrust coefficient. What happened? Previously, what we have seen C, particular characteristic velocity is directly proportional to the temperature of the combustion and the molecular weight, right? The molecular weight of the combined propellants, not individual, right? We are looking for the molecular weight of the propellant that is being, or the exhaust gases that is being generated after combustion, right? So to this, what we are getting the certain velocity, characteristic velocity. Now, the effect of adding a nozzle as well as its expansion can be added using the thrust coefficient, which is given by CF. Right? The choice of high temperature combustion may be limited by the structural properties, because as the temperature increases, the characteristic velocity increases. Now, due to this, what happens? Basic change. The temperature is limited by the structural properties, particularly the melting point of the material that we are being used under combustion chamber. So, as let's say the temperature is greater than the melting point of the material itself, what happens? Basically, they tend to melt. So, as soon as they melt, there will be a loss in pressure, particularly a breakage of your rocket engine. So, every time whenever we are designing a rocket, we are looking after the structural properties of the material that we are considering, and we are trying to improve or try to maintain the temperature that is being generated inside a rocket engine within those limits, right? And based on our requirements, we will be increasing them further by allowing the limits. And there are few methods through which we can control the temperature that we will be discussing under our further modules. Now, how do you compute a rocket engine performance? Right? For example, the performance of a rocket engine motor can be assessed by these three particular equations. First one is your thrust coefficient, right? And second one will be your characteristic velocity, and third one will be your force, particularly rocket thrust. Let me just rewrite. Now, try to understand. The first two are the equations that we have derived earlier, right? Now, coming to third, what is that? It is nothing but multiplication of my thrust coefficient as well as the characteristic velocity with the mass flow rate. With the mass flow rate will define my thrust, particularly the rocket thrust. Now, under the same, we will try to understand specific impulse, right? The exhaust velocity, whatever is going for rocket engine, is quoted or calculated in any book in terms of meter per second, right? But in a rocket, engineering the exhaust velocity is the most important, almost universally quoted in terms of specific impulse, right? And the apparent units, particularly in terms of specific impulse, are seconds. And the equation related to specific impulse and the exhaust velocity is given here, where V is nothing but my exhaust velocity and G is the acceleration due to gravity, as well as in metric units it is close to 10 meter per second square. So it is sufficient when faced with a velocity quoted with specific impulse to multiply by 10 in order to express it as meter per second. And there are three reasons in order to use this. First one is historical. So as the astronomers know, it is difficult to change historical usage. And the second reason is that the apparent units for a specific impulse being seconds, it takes the same value in the metric as well as the imperial systems. So the actual exhaust velocity emerges in the same units in which the acceleration of the gravity is quoted. So remembering the same, recently NASA has used imperial units, and this is a useful convention. There is also a plausible physical argument as follows. Now, an impulse. What do you call an impulse? It's a term used to describe the effect of a force, right? Effect of a force on a very short time on an object. As in, for example, a contact between a bat and ball. Now, as the bat hits a ball, the point at which the ball is in contact with the ball, a bat is in contact with the ball, will give out the impulse, particularly a small force onto the ball to push it farther, right? Now, the force that is being given or pushed onto the ball, particularly in shorter period of time, is equal to the momentum given to the object. Now, the specific impulse can be defined as an impulse given to the rocket by a unit weight of propellant, right? The specific impulse in any terms, if whenever we are defining, is defined as an impulse, particularly the force, right? The force that is given to the rocket by a certain weight of propellant, particularly denoted by I, which is nothing but in terms of ball is my F into dt, where my force is nothing but mass into exhaust velocity and dt while integrating, right? And for specific impulse, similar to my ball, right? Force into mg dt as it is. Now, the force is again rewritten as m into v. If you are cancelling it, the masses, what remains? Velocity, exhaust velocity to the ratio of the gravitational constant, particularly acceleration due to gravity. Now, where m is in our convention is the mass flow rate in terms of kg per second, and in order to derive the specific impulse units, which are Newton per second or Newton or kilometer per second, kilometer, kg meter per second, per kilogram per second, and cancellation of everything at the end produces the end of my seconds. And the specific impulse, which can be usefully considered as a measure of fuel efficiency of a rocket engine, that is the momentum that is being imparted, right? That is being imparted to the rocket per kilogram of the propellant that is being expelled through my exit area. Now, if the exhaust velocity is high, then the professional propellant efficiency is also high, which clears the form of equation of thrust, whereas specific impulse is proportional to the exhaust velocity and is a direct measure for a propellant efficiency, and it is convenient to express some of the other formulae in terms of specific impulse, such as like G is equals to G into ISP, particularly specific impulse, is equal to the effective exhaust velocity, the thrust, right? The thrust can be rewritten in terms of my mass flow rate into characteristic velocity as well as the thrust coefficient, which is also equals to the mass into exhaust velocity, which I can rewrite it as m into G and ISP. Now, if I want to write, let's say if I want, I can rename or rearrange them to form this. Particularly, thrust coefficient is equals to mg ISP divided by pressure, or let me just rewrite. So CF equals to mg ISP divided by characteristic velocity, right? And the characteristic velocity, if you are breaking down into further elements, gives you the same equation, which is mg ISP divided by pressure, the combustion chamber, into the throat area. Now, if you are rearranging the same, particularly CF into characteristic velocity is equals to G into ISP, if I consider for a unit mass flow rate. Now, on the next class, what we will be discussing are the nozzles through which we are working on, right? First, the type of nozzles and type of construction methods in which will be using to understand the nozzles and the nozzle performance and the type of nozzles that are available in terms of for rockets, right? Let me just recap a bit for the same thing. In this class, what we have derived, we have basically derived the thermodynamic thrust equation, right? Now, after the thermodynamic thrust equation, we have derived two particular elements, particular parameters which can be identified or which can be used to determine the rocket motor design, particularly thrust coefficient in terms of CF, denoted by in terms of CF, whereas characteristic velocity, see, right? Based on these two, what we have identified specific impulse, which is denoted by ISP, which is nothing but a measure of the flow of propellant per unit combustion rate. Now, based on these three, what we have discussed is basically the type of nozzles and what is the effect of thrust coefficient as well as the characteristic velocity with and without nozzle, and we have also deduced the understanding of specific impulse which can be used further ado, right? So, in the next class, we will be meeting again to cover the nozzles as well as the nozzle design. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.